All right, good morning, everybody. So today I plan to talk to start with section 9.3, which is about the infinite series. But I received a question here in the chat. I guess this is from your homework number 4. I'll try to help you with some of the problems here, and let's see. Okay, I'll do some similar problems from this. Just change the problems a little bit, so you can just little manipulate my examples so that you can try to answer these ones on your own, right? So let's see. Any do you want us to work on all of these problems, Brian? Though I guess yeah, some are similar. Yeah, let me pick. Okay, let me start with problem 24 there, or something similar to problem 24. So I'll do, say, n raised to 1 over, say, 4n plus 1. I hope this will not change the problem too much. Let me see. Yeah, I guess this should be fine. Okay. Now so we need to determine whether this sequence converges or not, right? So, well, in this particular example, we see that what we can do first, visual inspection or a quick check here. When n becomes large, the base becomes very large as well. So this will go to infinity, raised to what? Well, if n becomes large, 4n plus 1 becomes large. 1 divided by a large number, that will be close to 0. So essentially, what we will get in the sequence would be a very large number raised to a very small number, right? And that's infinity raised to the 0, which should remind you that of the indeterminate forms that you encountered in Cal 1. All right. So in order to determine whether this is convergent or not, I will use the Hitch theorem, which basically tells me that the limit of the sequence can be computed by looking at the limit of its real valued counterpart as x approaches positive infinity. And if it was a real valued function, such as my right-hand side over here, I know that the form would be infinity raised to 0, which is indeterminate. And remember how we dealt with indeterminate forms with an exponent before? So remember, we let the function to be y and take the natural log of both sides, right? So why do we take the natural log? We take the natural log so that the exponent will come down via loss of exponents, right? Because if you have an exponent inside a logarithm, that exponent can go down in front as a coefficient. So what will happen here? We'll get ln y is equal to 1 over 4x plus 1 times ln of the natural log of x, all right? And then I'll take the limit of both sides as x approaches infinity. But I'll be careful here, because now if we will be able to find what the value of this limit is, what we will find is the limit of ln y. But the original problem is looking for the limit of y. So that should remind us that there is a final step to be had after we compute the limit of this guy, right? But let's focus on evaluating this first and then do the post-processing later. So here, if I plug in, if I imagine x to be a very large number, the first factor will go to 0, right? And then the second factor will be the ln of a very large number, which will also be a very large number, which would be infinity over infinity times 0, which is indeterminate. But actually, a little rewriting of this function tells me, oh, I can look at it as a fraction instead of a product, right? So this guy would be better, because if I analyze this, I'll have infinity over infinity, which is one of the two forms where L'Hopital's rule apply, right? So now I have infinity over infinity. I can apply L'Hopital's rule. So the limit of the original ratio is just the limit of the ratio of the derivative. So derivative of ln x is 1 over x. Derivative of 4x plus 1 is 4 as x approaches infinity. Right? So basically, this is L'Hopital's rule from Calwan. You simplify your expression a bit. So we'll get the limit of 1 over 4x as x becomes large. Then we know that this will approach 0, right? Because the denominator becomes very large. 1 divided by a large number will tend to 0. Okay? So this example is a convergent series. Because it's a convergent series because the limit of an, basically, I'll just copy this. As n approaches infinity, right? But we knew that the limit that we computed before is 0, but that's not the final answer because that's the limit of ln y. But we're looking for the limit of y. So what we need to do is to use e as a base and raise it to whatever limit we got before. So this is something that you have seen in Cal 1. So hopefully you remember them now. So basically this is equal to 1. So we say that the sequence n to the 1 over 4n plus 1 converges to 1. All right. Let me see. Is that good? Okay, let me know if you have follow-up questions while I look at the problems that were sent. Kevin, you cannot say that. That is true. Though that is true, any number to the 0 power is equal to 1. That's correct, right? But here, it is not just any number raised to 0. It's a very large number, but it is not raised to exactly 0 because the exponent here is not exactly equal to 0. In fact, this guy, the exponent, will never be equal to 0, but it will just approach 0. So here, infinity to the 0 is not something raised to the 0 power, but a very large number raised to something close to 0. And a very large number raised to something close to 0 is indeterminate. We don't know what will happen exactly there because the exponent is not equal to 0. It's not exactly 0, but it's just a number approaching 0. That's why it's indeterminate. If it was a large number raised to an exact 0, then it's equal to 1. But here it's a little bit tricky because the exponent is not 0. It is something close to 0. So you cannot use that argument, Kevin, though that is true. But the thing is, it doesn't apply because the exponent is not an exact 0, but it is something that is very, very close to 0. I hope that's clear. And that's the tricky thing about limits. So you need to be careful when we write infinity to the 0. Here we mean that the exponent is something that is being very, very close to 0. All right. Maybe, yeah. So before I go there, here, so let me see. You know, it's already Friday, but even my numbering is off. Let's see this one, which is similar to what Kevin is pointing out. What if I have, say, 1 raised to the power n, if this is my sequence. Well, if you take the limit, this would be limit of 1 raised to n as n goes to infinity, and this will be equal to 1. It's easier to see if you write down the elements of your sequence. So if n is 1, you get 1. If n is 2, you get 1. If n is 3, you get 1. N is 4, you get 1, and so on. So it turns out that this sequence is just a sequence of all ones. So in the long run, it will just go to 1. All right. So the limit here is 1 is equal to 1. But taking this limit, but if you look at this limit here, right? If you look at this sequence, right? So if you want to get the limit of the sequence, you take the limit of 1 plus 1 over n raised to the 2n as n approaches infinity. If you try to directly plug in infinity here, you'll imagine, okay, what happens to 1 over a large number? 1 over a large number will go to 0, right? 1 plus something close to 0 will be something close to 1. So you have 1 raised to infinity, okay? So if you remember your topics from Cal 1, you'll say, okay, this is an indeterminate form, okay, 1 raised to infinity. But you might be confused right now because why am I saying that that's indeterminate when I encountered the same thing before? I have 1 raised to n and goes to infinity, and I get the limit is equal to 1. I didn't mention anything about indeterminacy. So why can anybody tell me why I ended up concluding that this is an indeterminate form, which is in direct contrast to what we had in the sequence in problem 17? They have the same forms. They have the form 1 raised to infinity, but what's the difference? Why problem 18 involves an indeterminate form and problem 17 does not? Anyone? Yeah, Christina, you're on the right track. Yeah, it's because of 1 over n. Because in the sequence in problem 17, 1 raised to n, the base is exactly 1, right? The base is exactly 1. But in problem 18, the base is not exactly 1, but a number very, very close to 1, right? So the first base is 1 plus 1, that's 2. Second base is 1 plus 1 over 2, so that's 3 halves. And then the third term is 1 plus 1/3, followed raised to the what? Raised to the 6, and so on, right? So here, 1 raised to infinity is not exactly 1 raised to a large number, but this is something close to 1, not exactly 1, but something that is close to 1 raised to infinity. So it's an indeterminate form. And if you do L'Hopital's rule, or if you just remember the formula from the lecture, you'll know that this is equal to e squared. Right? So basically here you have the indeterminate form, which is something close to 1 raised to infinity, it will converge to e squared. Meanwhile, here I have exactly 1 raised to the power n, that will converge to 1. And the main difference between them is that this guy, the base in problem 17, is an exact 1. The base in problem 18 is not exactly 1, but rather a number that is very, very close to 1. And that small discrepancy between 1 and 1 plus 1 over n means a lot, because the limit here is e squared and not equal to 1. All right. So I hope I didn't end up confusing you more, but yeah, that's the idea of limits. Base is exactly 1. Base is something close to 1. That's why it's indeterminate. Okay? Is that better, Kevin? About the others. Is that good? Okay, great. So we draw the distinction between those things, right? So, okay, I hope that's good. Let's do this one, problem 18. Okay, so we take the limit of 3 to the n over n plus 4 factorial. This thing involves the factorial, right? The factorial operator. And so we cannot transform it to a real valued function because factorials, at least for us, is only defined for positive integers. But if you want to take the limit, well, let's expand the term here. Well, the numerator will be 3 to the power n, so that means it's 3 multiplied to itself n times. Right, so here I'll have n times, while the denominator is n plus 4 factorial. So it's going to be, let me just slide this a bit. Okay. I'll have n plus 4 times n plus 3 times n plus 2 times n plus 1 times n minus 1, and so on. Okay, so basically here, which one is larger and which one grows faster than the other. So here you see that, okay, I'll compare the n terms here. So 3 versus very large n, 3 over n, the denominator wins. For large n, 3 over n minus 1, denominator wins. Actually, the denominator will always win, except for the last, the last two terms here, right? Because here you'll have 3. Oops. I'll have 3 times 2 times 1 over here, right? So essentially, the denominator will all for this guys, except for this the last two terms. But you have some extra factors in the denominator, so that means that the denominator is much larger than the denominator is much larger than the numerator. All right, so that means the denominator is much larger, so that means this will go to 0, right? Because the denominator grows a lot faster than the denominator. And I guess if I'm not mistaken, last time we had the hierarchy of, here we have an exponential, and then here we have a factorial. And we mentioned last time that factorials grow faster, a lot faster than exponentials. So that means the denominator grows a lot faster than the numerator, so this will tend to 0. Let me just check that if we have that in our notes. Yeah, I forgot to insert exponentials. So this is b raised to the n. Okay. So the slowest growth rate can be found for logarithms, followed by polynomials, then exponentials, and then factorials. Fastest growth can be observed for n to the n. All right. So you can apply that rule of hierarchy. If the denominator grows a lot faster than the numerator, then it's converging to 0. If the numerator grows a lot faster than the denominator, then it will diverge. It will tend to infinity. All right. Let me see what are the other questions here. Okay. Okay. And then probably, let's call it 19. And then probably a last one, problem 20. Okay, I guess I covered, Brian, the solution to all of the problems except problem 28. So you can pattern your solution to what I did here. Let me just give you something analogous to problem 28, but that's similar to the previous three problems here. But essentially, you're saying, what if we have, say, n plus 4 over over n raised to the, say, 11 over 2n. Okay, so now again, I'll take the limit of this guy as n approaches infinity. But if I will observe here a bit, what will happen? Well, this guy will go to 1, right? As n becomes large, they have the same degree. So I take the quotient between their leading coefficients. So coefficient 1, coefficient 1. So the limit is 1 over 1. So that means the base becomes closer and closer to 1. But the exponent, 11 halves times n, will go to infinity as n becomes large, right? So that means it's an indeterminate form, 1 raised to infinity. It's indeterminate, again, because the base is not exactly 1, but something that is close to 1. Because this guy is not equal to 1, but it will steadily becomes closer and closer to 1 as n becomes very, very large. Okay, so it's an indeterminate form, so I'm expecting to use L'Hopital's rule here. But you can recall my student lab class told me that Dr. Almus gave you this formula, that the limit of 1 plus 1 over n raised to the, sorry, 1 over an. No. It's, let me recall, 1 plus a over n raised to the b. Can somebody double check this formula? You know me, I hate memorizing formulas. So yeah, I will end up using L'Hopital's rule here. You can do L'Hopital's rule, as I think we did a couple of times last Wednesday, but I just learned earlier today that you were given this formula, and you were told to memorize this if you can. Is this correct? Can you check your notes? Because it will be helpful. It will save you a lot of time if you will remember this formula. Oh, I'm missing an n here. Okay, yeah. So I'm trying to use this in this problem instead of using L'Hopital's rule. So what you can do here is to simplify the base first. So you do the division here, n over n. I'll get 1 plus 4 over n raised to 11 over 2n as n goes to infinity. And compare this form to what the formula has, right? So here we can take a is equal to 4 and b is equal to 11 halves. So this limit is equal to e raised to a times b. So this would be e to the 22nd power. All right. So that means, yes, the sequence converges to e to the 22, right? And again, this is an example that the form of our term is 1 raised to infinity. More precisely, something close to 1 raised to infinity, or to a large number. It won't converge to 1, but it will converge to e to the 22. So be careful about indeterminate forms. Okay? And I hope now you have all the tools to answer the rest of the problems in that homework. So any follow-up questions on that? I hope that that will help you in solving the rest of the homework problems. Any follow-up question? Or any question about sequences? Because now I think we're done with sequences, and then we can go to infinite series. Nobody's reacting. Are you on weekend mode already? Oh yeah, good question, Kevin. Yeah, I guess this is one thing that we kind of skipped last time, talking about monotonicity. Yeah, maybe I can give you a couple of examples on this. Well, thank you for reminding me, Kevin. Monotonicity. Well, monotonicity just means that your sequence has a single behavior. It is either increasing throughout for all n's, that is a sub n is smaller than or equal to a sub n plus 1, or decreasing all throughout. Okay, so sometimes it's easy, actually, most of the times it's easier to conclude that your function is not monotonic, because all you need to find is an erratic behavior in the sense that you cannot order, the sequence is not ordered in increasing terms or in decreasing terms. And sometimes it's just looking at the first few terms will give you a nice idea about it. The more challenging part is to prove that it is indeed increasing or decreasing. Because the thing is, being increasing asks a lot. So this inequality must be true for any value of n, however big or however small n is. So it's more challenging to prove that a sequence is increasing or is decreasing than showing that it is not. Because showing it is not, you can just give me a counterexample. A term that is smaller than a previous one and a term that is larger than a previous one. That suffices as a proof for non-monotonicity. But if a sequence is monotonic, then you need to perform some tests, right? So let's look at some examples. So say for the following, let's determine whether the sequences are monotonic. Okay. Number one, probably let's start with the sequence 2 to the n over n squared. Now you can start by looking at the first few terms, and if you're lucky enough, then you can see a pattern, or you can see a counterexample. Because in this problem, we see that the numerator increases, right? And then the denominator also increases. So we don't know what happens to the quotient, because if you have a large number divided by a large number, we don't know what happens, right? So basically here, we're not sure if it is increasing or decreasing. Well, if you cannot do a mental analysis, then take a look at the first few terms. Maybe we'll be lucky, right? So when n is equal to 1, we'll get 2. When n is equal to 2, I'll get 2 squared over 2 squared, so I'll get 1. And then when n is 3, I'll get 8 over 9. When n is equal to 4, we'll get 2 to the 4th, which is 16 over 16. Oh, that's good. That's going to be 1. And so on, right? But here I can stop because I already found a counterexample. From the first term, it decreased, and then it decreased. But from the third to the fourth term, there's an increase. So it is not monotonic. So the sequence is not monotonic because it doesn't have a single behavior, either increasing or decreasing all throughout. And hence the term monotonic. It's mono, So that means it should have a single behavior. But here we have seen that sometimes it was increasing, sometimes it is decreasing. So it's not monotonic. All right. But I think eventually the function the sequence will be increasing because the numerator grows faster than the denominator in the long run. So the numerator will grow faster than the denominator in the long run. But we saw that in the first few terms for smaller values of n, there's a sort of an erratic behavior with respect to the magnitude of the terms. So this is not monotonic. All right. Now let's see this one. Say let's say I have 0.5 raised to the n all over n cubed. Let's see what happens here. Is it monotonic or not? Well, let's look at the behavior of the numerator. Well, the numerator will be decreasing, right? So you can say, okay, the numerator decreases, but the denominator is increasing. So what happens when the numerator keeps on decreasing, while the denominator keeps on increasing? What do you think will happen? What will happen to the fraction? Well, Kevin, be handled carefully and separately, because it's one thing that they will go to 0, and that's one thing that they will decrease. Remember, when you claim the function to be decreasing, it should be decreasing all throughout. But you're right, this will be decreasing all throughout because the numerator keeps on decreasing and the denominator keeps on increasing. These two behaviors have the same effect of decreasing the fraction, right? So that means you're right. This will be decreasing. And I guess you're also right that this will be decreasing to 0. But the stronger claim there is that this would be decreasing. So it is monotonic. Is monotonic. Or in particular, it is decreasing. Okay. Now, all we did in the previous two examples is to just play on our intuition, right? Look at the pattern or list the first few terms. That's fine. But let's look at this one. Let's say I have n squared minus 1 all over n. Okay. One technique that you can use whenever looking at the behavior of the function is to look at the derivative of its real valued counterpart. Because what happens here? Well, if you'll try a direct intuitive analysis here, the numerator is increasing, and then the denominator is also increasing, right? But the fact that the numerator is increasing tends to increase the fraction, and increasing the denominator will tend to decrease the fraction. So we don't know what happens, right? So because the top increases, the bottom increases, they have different effects on the fraction, so we don't know what the net effect would be, right? But so that means an intuitive analysis might not be sufficient here. But let's try a more analytical way. Well, you're right, Kevin. The numerator grows faster than the denominator, but that's in the long run. I don't know if that will happen for any n, because again, increasing and decreasing property of sequences rest on evaluating all the terms in the sequence and not just large n's or just small n's. The usual pitfall is for smaller n's. Because you're right, you can do asymptotic analysis and look at what will happen for large n's. But you might be missing some very sneaky pair of terms in the beginning of the sequence, right? So that's why for this one, since the behavior is not sure for any n, I'll try a more analytic approach. That means I'll look at the real valued counterpart, f of x, which is x squared minus 1 all over x. I will work with the real valued counterpart so that I can compute f prime. Because sequences do not have derivatives because they are just a bunch of points. But real valued functions have derivatives. So let's compute the derivative here. For that, I'll need the quotient rule. So I'll have x squared in the denominator, and then low derivative of the high minus high derivative of the low function. All right. And so this means, did I do it right? Low derivative of the high minus high. You already know it's Friday. I'm messing up my chain rule. So low d high minus high derivative of the low. So I got it reversed. So low squared low derivative of the high, there we go, minus high derivative of the low. So if you simplify, this is going to be 2x squared minus x squared plus 1 all over x squared. Or basically, this would be x squared plus 1 all over x squared. Right? Can you confirm that my quotient rule here is correct? Yeah, my calculation skills are failing me right now, but okay, is this good? Okay, thank you, Kevin. And you see that this is always positive for all x's greater than or equal to 1, right? X squared plus 1 all over x squared is always positive for any x greater than or equal to 1. Or you can go further and say that this is greater than 0 for any x, period, right? But I'm only interested for x's greater than or equal to 1 because I'm concluding something for the sequence, which allows only integers from 1 and 2, 3, and so on. So basically what we have seen here is that f prime is positive. Remember from Cal 1, a positive derivative means f is increasing. Since f is increasing for all x greater than or equal to 1, and again, you can be more general in your statement. You can say that f is increasing for any value of x, right? But here I'm only interested for all x's greater than or equal to 1. Then that means the sequence which is a smaller version of the real valued function is also increasing. Okay. Is that clear, everyone? All right, so this is, okay, so after I found the quotient, you mean after I applied the quotient rule, right? So here I use the quotient rule to evaluate f prime, and I have this, right? That's the derivative. And whatever x value I plug in into f prime, the denominator is positive because it's x squared. And then the numerator is also positive because x squared plus 1 is always positive. Positive divided by positive, so I get a positive number. So the derivative f prime is always positive for any value of x, In particular, it will always be positive for all x's greater than or equal to 1. I'm only concerned with x's greater than or equal to 1 because remember, we are dealing with sequences, and sequences takes on values from 1, 2, 3, 4, and so on, right? So you can say that, okay, the function f is increasing everywhere because the derivative is always positive for any x. And since it's increasing everywhere, if I restrict it to the positive integers, then it will still be increasing. All right. So that's why sometimes looking at the derivative will be helpful in determining whether it's increasing or decreasing. Okay. Now let's try one other way. So that's one way. Aside from intuitive analysis, you can take the derivative and see if it's always positive or see if it's always negative, right? If it's always negative, then you can say that, oh, the sequence is decreasing. Okay. Another technique, if the derivative doesn't work, is this. Let's try it for, say, 2 to the n over n plus 1 factorial. And at first glance, we know what will happen here. We know that factorials grow a lot faster than exponentials. So the denominator in the long run, with emphasis on the phrase in the long run, will become larger compared to the numerator. So that means this will converge to 0 by the hierarchy of growths, right? So this will approach 0. And since the denominator increases in the long run, I will have a decreasing function, a decreasing sequence, right? But I need to make sure because claiming that a sequence is increasing is a big deal. We're not just talking about what happens when n becomes sufficiently large. It should be true for any value of n. Okay, so if the terms of the sequence looks very apt for cancellation, you can do instead of looking at the derivative, because here actually we cannot look at the derivative here because factorials doesn't have a real valued counterpart, at least from our point of view. In higher maths, they have, but for now we don't know about their extension to the real valued case, but we cannot find the derivative here. So one thing you can do is to look at the ratio an plus 1 over an and compare it with 1, okay? So a sub n plus 1 is simply the n term where I will replace all n's by n plus 1. So here I'll get, let me get rid of the n plus 1. Let me just do n factorial, just to make it simpler. All right. So I will change all n's to n plus 1. So I'll have 2 to the n plus 1 all over n plus 1 factorial. That's the n plus 1 term. All over an, which is just 2n over n factorial. And then I'll simplify. I get 2n plus 1 over n plus 1 factorial times n factorial over 2 to the n. And then we can cancel 2 to the n by the first n terms in the top, or first n factors of 2 to the n plus 1. So we'll be left with the 2 on top. And here, remember, n factorial is n times n minus 1 and so on. But n plus 1 factorial is n plus 1 times n minus 1 and so on. So these guys will be canceled by those guys. So there will only be an n plus 1 in the denominator. All right. And then what can we say about this? Is it greater than 1 or less than 1 all of the times? Or there are some times that it is less than 1 and sometimes greater than 1. So what I'm trying to do here is to compare it with 1. Is there a uniform inequality that I can use here? So what's the relation there? Less than, greater than, less than or equal to, greater than or equal to, or what? Anybody? It's less than 1. Okay, that's almost right. Just be careful, Kevin. This is less than or equal to 1. Because when n is equal to 1, you'll get 2 over 2, that's 1, right? But after that, it will always be less than 1, right? So what we found here is that a sub n plus 1 all over an is less than or equal to 1. If you multiply both sides by an, we'll get an plus 1, an. And then the inequality won't change because an is positive, because an is a positive number divided by a positive number. And so we got this, which is the very definition of being a decreasing function. So the sequence is decreasing because a sub n plus 1 is smaller than or equal to an. Okay, yeah, it's right. It should be decreasing. Okay. So any other question about sequences? I guess those are 2 things that you can try. So derivative, actually 3 things. You can try intuitive analysis. Second is looking at the derivative, if it's always positive or always negative. Another trick is looking at whether the ratio is less than or equal to 1 or greater than or equal to 1. If you cannot conclude a single inequality, say you found that, okay, the left side is sometimes greater than 1 and sometimes less than 1, then it's not monotonic, right? So, but if you are able to find one single inequality that relates these 2 guys for any value of n, then you're good. It's monotonic. It's increasing or decreasing. Or another thing you can try is another possible solution method is to look at a sub n plus 1 minus an and compare it to 0. Just don't know if I have a quick example of that here, but yeah, I don't have a quick example, but I think you can see the rationale behind this test. Because if you will be able to conclude that an plus 1 minus an is greater than or equal to 0 for all n, right? So you'll simplify this guy. And if by chance you are able to say that, oh, that thing is always greater than or equal to 0, then you're good because now you can find that an plus 1 is greater than or equal to a sub n. And you can conclude that your sequence is increasing. On the other hand, if you found out that this is always less than or equal to 0, you can conclude that your sequence is decreasing. But if the left side is sometimes positive, sometimes is negative, then it is not monotonic. All right. So these are some tricks from algebra. That's why probably they are not specifically mentioned or highlighted in the lecture. But yeah, these are some algebraic techniques. Okay. Any other question about sequences? Now I have probably a minute. I'll take a peek at worksheet 15 and do an introduction about series. And I'd like to start with this sort of a joke or something, or a meme. So an infinite number of mathematicians walk into a bar, and then the first orders a beer. The second one orders half a beer. The third one orders a fourth of a beer. And then the bartender seems to be pissed off and say, okay, here are 2 beers for all of you guys. And actually the bartender here wouldn't be wrong. And we'll see next time why. You see here that, yeah, it turns out that the bartender is also a mathematician because he knows how to sum up a series. Because the pattern here is that a mathematician orders half of what the previous mathematician ordered. So you see that, okay, So if you will sum up the orders of this infinitely many mathematicians, it seems that, okay, I just need 2 beers, and that's sufficient for infinitely many of them. And we'll see next time why. But this is one topic that probably intuitively doesn't make sense at first, because how come that you take the sum of infinitely many number of terms, but then there's a possibility that you get a finite answer. And we'll look at cases or tests that will let us know if there's a finite sum or if not, or there's no finite sum, right? And then let's analyze this problem about the infinite number of mathematicians next time, all right? So, oh, by the way, before we leave, have you gotten your scores in FRQ? Oh, great. So if you, yeah, kindly take a look at them. But I think there's a change in the policy a little bit now because our lead TA just told us that all regrading requests should be sent to the lecturers. So if you have some, if you want some parts of your tests regraded, or if you feel that you should have gotten more points for a certain problem, you should direct your questions to Dr. Almas. But I think some of you might be hesitant to do that at first. You can consult me, and then I'll let you know what I think. And then after that, you can email Dr. Almas. But you can also go directly to Dr. Almas because that's how it should go. But I can be an intermediate layer if you want to make sure and check with me first before you bring it up to Dr. Almas. But ultimately, it will be Dr. Almas's call whether to regrade your test or not. Okay? So have a good weekend, everybody. And then let's see each other again on Monday. We'll start with section 15. Oh, go ahead, Lucas. Do you have a question? Okay, that's fine, Lucas. Pressed by mistake. Okay, no worries. Okay, bye, everybody. See you Monday. Have a good weekend.